Well, as of now, we are live and we will be starting the class. Some people are absent, but we can't help. So, all right. So today we'll be talking about sequences and series and clearly talking about partial sums, convergence of sequences and series, geometric series, the notions of bounded and monotonic sequences. And then we will introduce the divergence test for series. That's what we get. Can everybody see this and hear me? Good.
Yes, sir.
Thank you. So the first thing, again, let's go about the partial sums. Partial sums of series. So if we assume we have this series sum n from 1 to infinity, this means add all terms from the first to the last one that goes to infinity of an. The partial sums are denoted Sn and are equal to A1 plus A2 plus up to An. So the partial sum, the nth partial sum, is the sum of the first n terms of the series. That's what we defined last time. All right. And recall that again. And we say that the series, converges. We talk about this too. So today we repeat it again. We say that the series converges if and only if Sn has a limit L, a finite limit, right? And we write sum n from 1 to infinity An equals L. So if we have a series sum n from 1 to infinity of An, the partial sums of that series are denoted Sn, S with index n, and that's equal to A1 plus A2 plus up to An, the sum of the first n terms of the series. That Sn, which is the partial sum, is a sequence. This is actually a sequence, as we said last time. And therefore, we can look for the limit of that sequence. If we find out that that sequence Sn has a limit that is not infinity, then we conclude that the series converges and we set it equal to the limit of the partial sums. So that's how we handle infinite sums. We take the partial sums, we figure out what the limit of the partial sum is if we can. If it's finite, then we say that the series converges and that it is equal to the limit of the partial sum. example, the famous example will be the geometric series. This by itself is something that you need to memorize. Geometric series. So the geometric series is defined as sum n from 0 to infinity a times r to the power n, where a and r are given real numbers. So here we are dealing with the sum of a number multiplied by a power of another number. So a is a fixed number, r is a fixed number, r is raised to the power n, and make sure you see that here this term starts with n starting at 0, right? And so for this sequence, we will write down what Sn is equal to, and we will find the limit of Sn. And we will give a general rule that when you see, you can just decide that this series converges without having to work it out. So let's say Sn here for this series. Remember the definition? We said Sn is the sum of the first n terms, right? So if we're starting by 0, n equals 0 here, so that's going to be a0. Inside this is what we call an, right, for this sequence. So a0 plus a1 plus a2 plus an minus 1, because if I start by 0 to have n terms, I need to stop at n minus 1. So these are the first n terms of that series. Now put in each of them as is, a0, and here we will be repeating how to read the indexes. So a0 will be, meaning put n0 in this formula. So that would be a times r to the power 0. R to the power 0 is 1, so that is a, plus a1, that'd be n equals 1, so that a times r, that's a times r, plus a2, that means replace n by 2, that's a times r squared, plus all the way down to a to the power n times r to the power n minus 1, because we replace n in the last one, we replace n by n minus 1, that is a r to the power n minus 1. So this is what the sum of the first n terms is equal to. Now there is a trick to find a formula for this thing. Let's say we multiply Sn by r. So we write here r times Sn. We multiply Sn by r, all right? That's a trick to find the formula of Sn. So multiply Sn by r. When you do that, each of the terms gets multiplied by r, right? So this becomes AR plus A, this becomes R squared plus A, that becomes R cubed, plus all the way down to A R to the power N, because when you multiply R to the power N by minus 1 by R, what you get is R to the power N. And now when you look at these two things written next to each other, you can see that the difference between every pair of them is just R, and you have a common factor of R minus 1 here. When you pull it, A times R minus 1, when you pull it out, you're left with 1 minus R. Here, if you pull out AR squared, you're left with 1 minus R. Same here, if you pull out AR, you're left with 1 minus R. If you pull out A here, you're left with 1 minus R. So if I subtract these two things, I actually get a common factor of 1 minus R in each of the terms. And that's what I'm going to do to see what's going to happen. So Sn minus R Sn. So I subtract the two things, and then I do just what I just told you. I take the first two and factor out 1 minus R. So this is A times 1 minus R plus this here is AR times 1 minus R. Right? Do we agree? Okay. So you could do that. Here, R squared, 1 minus R, and so on. When you get there, you get AR to the N minus 1, 1 minus R. So you see something like that can happen, right? But if you look carefully at this also from the other side, look here. Look at this first number, right? What is that here? Is it the same thing? Right. Look at this guy. Is it that one? Okay. Look at this one. That's probably the next one that is coming here, right? This guy here is the previous one that you had here before this one. So technically, actually, when I'm subtracting, I could do this and still get something, but it's not going to be as helpful as if I just said, okay, that subtraction gives me the first term is A, then AR cancels, then AR squared cancels, AR cubed cancels, everything cancels except the one that I have here. And it comes with a minus. You see the magic? So there are many things that you can do that might turn out to be useless. So you don't always just jump and start doing something because you're feeling that this thing is going to work out, right? So here, what we just realized is if we go ahead and we look at the two things that are written there, then this term cancels with that one. This term cancels with this. This term here cancels with the following term that comes here. And the last term up here cancels with the previous term before AR to the power N is AR to the power N minus 1. So they all cancel. And I remain with the first term and the last term there. So technically, what you get here is that Sn minus R times Sn is nothing but A times 1 minus R to the power N. And this left-hand side is actually nothing but 1 minus r times Sn. You see that? Do we all agree with this? So I factor out Sn here, and therefore I can use this and that to solve for Sn. So the sum is A times 1 minus r to the power n over 1 minus r. And this is a formula that you can memorize and use in any exercise that you have. Okay, so if I want to add the first n terms of a geometric series with the first term being with n equals 0, that sum, which is this, is equal to A times 1 minus r to the power n over 1 minus r. That's it. Now let's get an example inside the example. Yeah, that's crazy, right? Example of the example. So you have one plus 0.1 plus 0.01 plus 0.001 plus and so on. If you have something like this, let's say you keep adding 1 0 here and then continue adding, and they ask you what is this sum equal to, or what is the sum of the first n terms of this. So you would say this thing is actually a sum n from 0 to infinity of 1 over 10 to the power n. You see this? It's the first one is 1 when n is 0. The second one is 0.1 because 1/10. The third one is 0.01, 1 over 100. The third one, the fourth one is 1 over 1,000, right? And so on. So if you have a sum like this, which is actually 1.11111111111, and right? That's how you'll be writing down this number. You would say it's 1.11111. It continues, right? Which is 1 plus 0.1 plus 0.01 plus 0.001. And we want to figure out how we can cut this thing, get the sum of just the n for the first n terms. So here, A is 1 because the number in front of r to the power n is A. That's A equal 1. R is the number that is raised to the power n, so that is 1/10. And so Sn is going to be A times 1 minus r to the power n over 1 minus r, which is A1 times 1 minus r is 1/10, right? That's 1/10 to the power n divided by 1 minus 1/10. So this is what Sn will be. And then you can do the algebra here. So you're gonna get that this is 10 over 9 times 1 minus 1 over 10 to the power n. So that's what Sn will be in this problem. And then you might ask yourself, because we were talking about convergence earlier, what's the limit of this sequence? So the limit of Sn in this example, of this Sn in the example, is equal to the limit as n goes to infinity of 10⁹ times 1 minus 1 over 10 to the power n. And we try to find this limit. You guys help me. What's this limit equal to? 1 over 10 to the power n goes to what when n goes to infinity? I can't hear you. Your microphone is not on. Can anybody tell us what the limit of this sequence is going to be equal to?
10⁹.
The infinity?
Huh?
Would it be infinity?
Okay, now let's go step by step. What is 10 to the power n when n goes to infinity?
Infinity, right?
Right, 1 over infinity.
0.
0, 1 minus 0
1.
times 10⁹.
10⁹.
So your answer is 10⁹. And now you can check on this example to see if the theory that I was giving there was a lie or not. You can take your calculator and check 10 divided by 9. You would see that this is what you get, which is what is there, the sum of all those terms. So this is an example that shows you that the theory just didn't come out of the blue, right? It works on concrete things that you can do for simple fractions. This fraction is equal to that sum. So here we will say that sum n from 0 to infinity, 1 over 10 to the power n is equal to 10⁹. And therefore we say that this series converges. It converges because this limit is finite. Any questions?
Do you think you could explain how you got that limit again?
Again, take the limit, 10 to the power n, when n goes to infinity, 10 to the power n goes to infinity. 1 over infinity is 0. 1 minus 0 is 1. 1 times 10⁹, 10⁹.
Thank you.
Any other questions? Now, in general, for geometric series, so limit sum n from 0 to infinity of a r to the power n is equal to a over 1 minus r when absolute value of r is strictly less than 1. Otherwise, it diverges. Why would that be the case? Because we will take the limit here. We take this limit when absolute value of r is less than 1, r to the power n goes to 0. Because when you take a number that is less than 1 in absolute value and you multiply it by itself infinitely many times, it gets so small that it goes to 0. Right? So that would be 0, 1 minus 0, 1 times a. So the limit is a over 1 minus r, which is what I wrote here. But if the absolute value of r is not less than 1, then this limit either doesn't exist or is infinity, okay? Therefore, we say that the series diverges. The geometric series diverges when absolute value of r is not less than 1. It converges to a over 1 minus r when absolute value of r is less than 1. And this is an example of that. Questions? Okay, if there is no question, let me give you an example to solve. So exercise. So 1, find Sn for sum n from 0 to infinity, 1/3, 2/5 to the power n. So what would Sn be equal to? Anyone, you can just tell me and we write it down. So based on the formula that you have, we said Sn is a times 1 minus r. Sn is a times 1 minus r to the power n over 1 minus r. So what would be Sn in this case?
Would it be 1/3 times 1 minus 2/5 to the power n over 1 minus 2/5?
That's it. And now you do 1 minus 2/5, that's 3/5. So this gives you 5/9 times 1 minus 2/5 to the power n. Right. Now second, find the value of sum n from 0 to infinity, 1/3, 2/5 to the power n. So it's two different things they can ask you over there. Either find Sn or find the value of the sum. So in this case, we said the sum is equal to a over 1 minus r if absolute value of r is less than 1. So to answer this question, you start by figuring what is r in this question.
Yeah, r is 2/5.
2/5, all right. So that's r is 2/5, which is positive and less than 1. So absolute value of r is less than 1. So we have it. Therefore, the sum n from 0 to infinity, 1/3, 2/5 to the power n is equal to 1/3 over 1 minus 2/5. And this is equal to 1/3 over 3/5, which is 5/9. Any questions? Hopefully this is clear enough for everybody. Two. Properties of converging series. So something very helpful in some problems. So if I have sum n from 1 to infinity an converges, and sum n from 1 to infinity bn converges, then sum n from 1 to infinity of an plus or minus bn, doesn't matter which of them, this is going to converge. And equals sum an plus or minus sum of bn. So this sum, if each of them converges, this sum is going to converge and be equal to the sum of the first guys plus the sum of the second ones. So the sum of the difference will also converge to the difference of the two sums, right? But that is only if we start by having both of them converging. If they don't converge, then this rule doesn't work, right? Now, the other guy is, now if sum of an converges, but sum of bn's diverges, then notice that I didn't put the limits of the summation, right? So it doesn't matter whether it starts at 1 or 2 or 0 or 3. These properties are always going to work. So then sum of an plus minus bn, this is going to diverge. If one of them is divergent, then the sum is going to diverge, right? But if both of them are divergent, then you don't know, because the sum might be convergent, okay? Because the things that make them diverge can cancel each other when you add them. Does that make sense? So let's say, for example, C, warning, right? Never try that. Some people try that off sometimes. If you have sum n from 0 to infinity of 1/3 to the power n as cosine of n, for example, and sum n from 0 to infinity 2/5 to the power n minus cosine of n, for example, this thing diverges. Why does it diverge? Because the sum of 1/3 to the power n converges and the sum of cosines diverges. Okay? Same reason here, this diverges because sum of 2/5 to the power n converges and sum of cosines diverges. So both of them diverge. But when I add the two of them, so this diverges. But sum n from 0 to infinity, if this is an and that is bn, an plus bn equals sum n from 0 to infinity. And when you add them, cosine and cosine cancel. So you have 1/3 to the n plus 2/5 to the power n. This converges and that converges. This one converges to 1 over 1 minus 1/3, and that converges to 1 over 1 minus 2/5. So that the sum converges. So the sum of two diverging sequences turns out to be convergent. All right. And some sums will be divergent. Some sums of diverging series will be divergent. So the only good cases are this and that, where you can decide right away. Does that make sense? Any questions, please? Now, using this rule that I just wrote here, I want you to do this exercise for me. Find the value of sum n from 0 to infinity, 2/3, 1/2 to the n, minus 3/7 to the n. You get 4 minutes for that. Anyone with an answer?
I got -5/12.
Okay, can you brief us on your steps?
Yeah, so I separated the two sums and then
That's the first step. You separate the sums. Let me follow with you. I'm writing down.
all right.
So you write sum n from 0 to infinity, 2/3, then 1/2 to the power n minus sum n from 0 to infinity, 3/7 to the n. That's using this first rule here. Because each of them converges, then the difference will be equal to the difference of the sum. Then what next?
Then I substitute in a over 1 minus r for both of them.
Correct. So that's the next thing that you're using. You know that each of those sums is equal to its own a over its own one minus its own r. So a here is what?
2/3.
So that would be 2/3, and then 1 over 1 minus.
1/2.
Correct. Then minus.
It was 1 over 1 minus
Because a is 1, and then r is
it 3/7.
7. That's it. So that's how you do. And now you figure out with the algebra. If you're good at algebra, you get the right answer from here. If you're not good, it's not that bad. So we compute this. That's going to be 1 minus 1/2, that's 1/2. So 2/3 over 1/2, that's 4/3. Then you have minus 1 minus 3/7, that is 4/7, and 1 over 4/7, that's 7/4. So when you do that, you get 16 minus 21. So it minus 5. Is that so?
Yeah, that's what I got.
Minus 5/12. So that's the answer. Minus 5/12. Excellent. Any questions? Any questions about this? Now, all right. The other thing that we might do in this question is that the sum might not start at 0. When it doesn't start at 0, you gotta somehow work it to make it come back to a sum that starts at 0. Okay. Let's say we need to find sum n from 1 to infinity of 2/5, 3/2, not 3/2, but 3/5 to the n. Let me even say to the n plus 2 to make it more interesting. And we need to find the sum. And so here, the first thing you need to see in this problem is that n here is 1, not 0. So it starts at 1. To be able to apply our formula, you need to have an n that starts by 0. So that's the second level of the problem. Thank God, 3/5, that's R, 3/5 is the, in absolute value, less than 1. So we do know that this thing is going to converge. Now, how do we figure what the limit is? We shouldn't just write down A over 1 minus R, because the formula A over 1 minus R is for a series that starts with n equal 0. I can't emphasize this enough. So be very careful with that. If it doesn't start by n equals 0, make sure you bring a new variable there that starts at 0. What do I need to do to this number to get it to 0? What do I need to do to the number I have here to get it to 0?
Do you move it over to the other side? Like set a new variable that equals n minus 1?
Good. So I need to subtract 1. That's the word. So you need to subtract 1. So I set here a new variable, k equals n minus 1, to make sure that this new variable is going to start at 0. And it's same as saying that n is k plus 1. This is called the substitution. That's the kind of substitution that you do in integrals. It's just that here we are adding, and so we replace the variable the same way we do when we do U substitution in integration. You remember that? So here we get this new variable that we want to start at 0. If we wanted to start at 0, then we need to subtract the number we have here. Now we can rewrite this sum, and that will be k going from, when n is 1, we plug it in here, k is 0. That's why we made this transformation. When n is 1, we get k equal 1 minus 1, 0. When n is infinity, well, infinity minus 1 is infinity. So k goes from 0 to infinity. And then you got 2/5 and then 3/5 to the power n is k plus 1. So you replace n by its value. N is k plus 1. So I replace n by that. That's n. And then you had a plus 2. So that plus 2 is still there. So here what you do have is n plus 2. So in this substitution, we replaced n by k plus 1, and we get this in the end. And that is equal to sum k from 0 to infinity of 2/5 times 3/5 to the power k plus 3, because 1 plus 2 is 3. So now you have the whole thing in terms of k, and then you have this plus 3 here. This plus 3, we can take it off because we need to have a formula sum k from 0 to infinity ar to the power k. So the same thing that is here is the thing that needs to be in a power. Because we have this extra plus 3 here, we're going to remove it. The power comes down by 3. So I'm a sum k from 0 to infinity 2/5, and then I take 3/5 to the power 3 off of that, and I'm left with 3/5 to the power k, and this is what I want. I want power k, and I want to have k here. These two things must be same. Does that make sense? So once I do that to make sure I have the same thing here and here, the power goes down here and it gets into A, and this is the new A for this sum. And therefore that sum is equal to A over 1 minus R, and that's the R from the beginning. And that is A is 2/5 times 3/5 cubed over 1 minus 3/5. That's how you will find the sum in this case. And so 1 minus 3/5, this is 2/5, right? 2/5 over 2/5, they cancel. So the answer here is 3/5 cubed, which is nothing but 27 over what? 125? Is there any question about this? Now, the last thing that I wanted to talk about here is what we call monotonic sequences. So a sequence AN is said to be monotonic if and only if starting from n larger than some value a n plus 1 is larger than a n, or and in this case we would say that it is increasing, right? Or from n larger than some n, a n plus 1 is less than a n, and in this case we would say that the sequence is decreasing. Right. So a monotonic sequence is a sequence that is either increasing or decreasing. A sequence is increasing if you can have a n plus 1 larger than a n for all n that are larger than some given number. Sequence is decreasing if you can have a n plus 1 less than a n for some large n. And this must be true for all values of n that are larger than that given n, okay? So here, let's say we take an equals n cubed over n to the 4th plus 1, for example. And the question is this a monotonic sequence? Now, the trick in the answers often is, you know what increasing and decreasing mean in calculus. You know that if it's a function, when the derivative is negative, it is decreasing. When the derivative is positive, it is increasing. So often in the problems, instead of trying to show this thing that I wrote here, we instead take the derivatives if the function is nice enough and we can take the derivatives. Okay, so here we could say trick an is increasing if, let's say, you have an equals f of n and f prime of n is positive for n larger than a capital N. An is decreasing if you have an as a function of n and the derivative f prime of n is negative for n larger than some n. So these are the two things that are often used in problems, right? So in this example, I'm going to use just that. So my an is this. So to answer this question, I will say f of n is n cubed over n to the fourth plus 1, and I take the derivative of that function f prime of n. This is a quotient rule. Quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top over the square of the bottom, right? So that is going to be 3n squared times n to the fourth plus 1 minus 4n cubed times n cubed over n to the fourth plus 1 squared. That's how you find a derivative in this case. And that is 3n to the power 6 plus 3n squared minus 4n to the power 6 over n to the fourth plus 1 squared, which gives us f prime of n 3n to the 6 minus 4n to the 6, that's minus n to the 6 plus 3n squared n to the fourth plus 1 squared. Now, when you have this f prime of n, you can see that n to the 6 is the dominant term for the numerator. N to the 6 is a lot larger than 3n squared. And the sign here is negative, so this thing is going to be negative. The bottom is always positive. All right? And you can pick, you can try another way to show that it's negative, but it's really not necessary in problems like this. You can see that this number, n to the 6 is the highest power of n, so you will go based on that, and it has a negative, so it's going to be negative. Does that make sense? You have a question, please ask. If I just have the silence, I don't know if I'm really getting through to you. Is it okay there, Jonathan? Eric? Sydney? Are we okay?
I can see you, but everybody else seems to be frozen up.
I just don't get it. So, Keziah? Gage? Chase? I don't see them. Elizabeth? Can you hear me, Autumn?
I can hear you.
I
Okay.
can as well.
All right. Okay, so this is negative as we said, so which means that the sequence is decreasing. And if it's decreasing, that also means that it is monotonic. So why is it important, that notion of being monotonic? Let's get the next notion that helps with that one. We say that a sequence AN is bounded when only if absolute value of AN is less than M for all N and some fixed M. So if there exists a number M that is larger than all terms of the sequence, we say that the sequence is bounded, right? In absolute value, right? In the example that we had here, we had AN equals N cubed over N to the fourth plus 1. We do know that 0 is less than N cubed over N to the fourth plus 1. And this thing is less than N cubed over N to the fourth, because if I remove 1 from the denominator, I get a larger fraction. If I remove this one, I get a larger fraction. So this is strictly less than N cubed. Over here, you can put or equal, right? N cubed over N to the fourth. And N cubed over N to the fourth is equal to 1 over N. And 1 over N is always less than 1, or at most 1 when N is equal to 1. So you have that 0 is less than AN less than 1. So absolute value of AN is less than 1. So AN is bounded. So this series, this sequence is bounded. Bounded because we can put all the terms of that sequence between two numbers. Are we good?
Yeah.
My thinking is that many people are just not in this class. They are connected and they are not with us. And I don't think that's a good thing to do. Because I call and you don't answer me. If you don't answer me, that means you're not here, even if your camera is there. Class participation is a requirement. It's not just presence. Now, with the notions of boundedness and monotonicity comes a theorem that says, if I can't find the limit of a sequence, I can perhaps know whether it exists or not. And the theorem says here, any bounded, which is what we just explained, and monotonic, which we just described, which means increasing, or decreasing. Sequence, any bounded and monotonic sequence converges. And converges means has a finite limit. So example, our sequence that we had in the previous problem, an equal n cubed over n to the fourth plus 1 is bounded. We have shown that. And it is monotonic because it is decreasing. Thus, it converges. So we know that it converges without even having the limit, right? We know it converges because it's bounded and it is monotonic based on this theorem. So on the other hand, we could actually find the limit of this sequence. Limit of an as n goes to infinity equals limit as n goes to infinity of n cubed over n to the fourth plus 1, which is limit as n goes to infinity of n cubed over n to the fourth, the ratio of the highest powers of n, which is limit as n goes to infinity of 1 over n, and this is 0. Of course, it has to be a finite number because we already showed here that it converges. If it converges, it means that the limit exists and it's a finite number. And we just found that it's 0. Well, the last thing today is going into the series. Divergence theorem. So the series is the easiest of the theorems that you have for series. Sum n from 1 to infinity an diverges, and it's always used to decide that the series diverges. Diverges if limit of an as n goes to infinity is not equal to 0 or does not exist. So if I have this infinite sum, the limit is not 0 or doesn't exist of an, one term, then we conclude that the series diverges. Warning. If we compute this thing and we find that limit of an as n goes to infinity equals 0, don't use this test. So the test is only to conclude divergence. If you find the limit and it's 0, then it was just a waste of time. You look for something else to answer the question. Example, you get sum n from 1 to infinity n squared over 3n squared plus 1. An here equals n squared over 3n squared plus 1. Limit of an as n goes to infinity equals limit as n goes to infinity of n squared over 3n squared plus 1. This is 1/3. And 1/3 is not 0. Thus, by the divergence test, the sum of n squared over 3n squared plus 1 diverges. That's it. If you get another example, if you have sum n from 1 to infinity of sine of 1 over n, here an is sine of 1 over n, limit as n goes to infinity of an equals, when n goes to infinity, 1 over n goes to 0, sine of 0 is 0. Oh, that's the warning. So can't use the theorem. You got to use something else. Because this limit is 0, you cannot decide whether this series converges or not. The other example will be sum three-fifths to n here, and then 3n over 5 minus 1 to the power n. Here you would have an is 3/5 of n times minus 1 to the power n. That's an. And the limit of an as n goes to infinity does not exist. This limit does not exist because negative 1 to the power n will be fluctuating between negative 1 and 1, negative 1, 1, negative 1, 1. And then you go either to infinity or negative infinity, infinity, negative infinity. So there is no limit. The limit does not exist. Therefore, we can use the theorem, the series diverges. Any questions?
No.
All right, so this is probably the end of the time, right?
Looks like
All right, so, and that's pretty much all I had. So if you have any questions, feel free to ask. If no question,
I have a question.
yes, sir.
So the series will only converge if the limit is infinity or 0?
We decide divergence again. That's the warning here. So we only decide that it diverges. So if the limit is 0, that's right here.
Yeah, but if it doesn't diverge, then it converges, right?
This decision doesn't tell you whether it diverges or not. It says don't use the theorem. The theorem cannot help. Okay? So we don't know whether it diverges or it converges.
Oh, okay. I get it.
That's the thing here. So, and here as in this one, you see the limit does not exist, and we conclude it diverges. We know it diverges. Here the limit is 1/3, it's not 0, because we say in the theorem, so it's two cases. It's either the limit is not 0 or it doesn't exist, right? When the limit doesn't exist, the series diverges. When the limit is not 0, the series diverges. But when it is 0, don't use this theorem, because you don't know whether it diverges or it converges. Because there are cases when the limit is 0 and the series converges. There are cases when it's 0 and the series diverges, all right? I can actually give you two such examples right now. So let's say you get sum 1 over n from 1 to infinity, okay? So an equals 1 over n, limit of an equals 0. Then I have sum n from 1 to infinity, 1 over n squared. An is 1 over n squared. Limit of an is 0. These two series are very different. They are part of what we call the P series. Here it's P series with P equal 1. It diverges. We know that. We will prove that. This diverges. This is P series with P equal 2. It converges. We know that. We will prove it. You see? So limit is 0, it converges. Limit is 0, it diverges. So when the limit is 0, you cannot decide. That's why you shouldn't use the theorem. That makes sense now?
Yeah, I get it.
Okay. Any other question?
On that first example you gave, you got the limit of 1/3. Could you explain how you got that?
This?
Right. Yeah. You got that 1/3. Right.
That's n squared over 3n squared plus 1, ratio of polynomials. So we take the ratio of the highest powers of n. That's n squared over 3n squared. The n squares cancel, you have 1/3.
Gotcha.
It's same as this other example, right? We take the highest power of n cubed over n to the 4, they cancel, you have 1 over n, and then you get the limit. But in this case, you got n squared over 3n squared. The n squares cancel, it's just 1/3, right?
So does that plus 1 just go away?
Again, same as in the other example, we always take care of the highest powers of n when we have a ratio of polynomials and we're looking for a limit. Anything else that is written next to that is of minor interest because it's always smaller than the highest power of n. Does that make sense?
It does.
Yeah, because here, this thing is very small compared to that. Let's say you take n equals 100, right? This is 100 squared, 10,000, 30,000. What is 1 next to 30,000, right? So the most important thing is this one. And therefore, we take that over this, and we get that it's in 1/3. Same thing in this other example. This one is very small compared to that. When n goes to infinity, because we are talking limits, when n goes to infinity, which means n is very large. So when n is very large, this thing has no power compared to n to the 4. That's why when you're doing limits, you always take, for polynomials, the ratios of the highest powers of n to find the limit. Other questions? All right, if there's no more question, then we are done for today, and I'll thank you and say see you next week. So you will have you have the other suggested problems that are already posted online for this topic, and it covers the material that we have covered. So usually what I do is I do put the problems that will be applications of what we do in class, so that if you do that, you perhaps on track for the class. And if you don't, well, then you sit and you think it's easy until you see the test. Mathematics are always easy when somebody else is doing it. You say, oh, wow, this is so simple. I could do this, but you didn't, right? So please practice. When you practice, you are sure that you know. All right.
Thank you.
You're welcome, sir. I'll see
Thank
you.
you.
Mhm.
Thank you.